so much for the kind introduction and the invitation to give this seminar. I want to talk about what happens when control changes the data that we're receiving, and in particular about safety under interaction-driven distribution shift. And with this talk, I have mainly three goals. My first goal is to introduce those of you that haven't heard about it yet to conformal prediction, which is a statistical tool that has become quite popular recently and is used for uncertainty quantification. My second goal then is to show you how conformal prediction can be used for safe control design in dynamic environments. And here I want to summarize a little the work that we've been doing over the past years. And third, and this is really the main part and the latest work that we've been doing is then on continuing along those lines, but using instead robust versions of conformal prediction for safe control design in interactive environments. And this will really be an instance where control changes the data that we are receiving through interaction between agents. By the way, just quick confirmation, can you see my cursor if I point at something, my mouse cursor? I don't hear anyone, so okay, perfect, good. Just because I will point at a couple of things. All right. So this is the high-level overview, but before I get into the technical details, I want to motivate a little more on a high level the research that we're doing in my lab. And I'm very interested in autonomous systems broadly. And those are, as you know, really control systems that operate autonomously in complex and open-ended environments. And the research we do in my lab is particularly motivated by applications in autonomous driving and robotics. That's also why I'm here at ICRA right now in Vienna, but also more recently in wildfire prevention and disaster recovery missions more generally. But there are many other applications. Some of you work on these, for instance, in space exploration, warehouses, agriculture, or even smart cities. And I think all these examples really demonstrate the potential impact that autonomous systems research can and will have in the future. Now, what we have observed over the past years is an increase in the availability of data and particularly compute. And this has led to accelerate the progress that we've been doing in order to build autonomous systems. And I've shown three over here. There are many others, but here you can see Boston Dynamics robots, Tesla cars, and drone flaps. And as you can see, here these systems really perform highly challenging tasks with ease. However, the question I would like to ask you, and that I also ask in my lab, is do you think that we really have all the theories and tools in hand to build autonomous systems that are also safe? And I would argue that the answer to this question is no, simply because at the same time, we've seen a lot of failed demonstrations. Boston Dynamics robots crashing, Tesla cars colliding, and we've seen drone fleets collapsing. So the answer really is a clear no. Nonetheless, we have moved ahead and we've actually deployed these systems in the wild. But not surprisingly, we're still facing issues. Here, for instance, from Los Angeles, where one of the many Waymo cars was passing by a police standoff where a criminal was being apprehended. Certainly something undesirable. Another example here from LA, where a delivery robot collided with a disabled man on the street. Certainly something we don't want to see. And yet another example here where a robot is headbutting a person in the crowd. Clear safety issue, also something we don't want. Now, there are many more of these videos. That's not really the point of showing this. The point is that we should start thinking about the reasons why we're facing these challenges. And there are many reasons, but today I want to focus particularly on three of them. First, we're employing increasingly more AI in our autonomous systems. And as you know, AI models can be quite complex and for that reason, difficult to reason about in terms of their safety, and they're hence difficult to verify. And this is here referred to as the AI's Achilles heel. Now, another reason are distribution shifts. And on a very high level, distribution shifts are when the conditions during design and deployment time are different. For instance, we may be collecting data during sunshine, train some perception algorithms based on that, but then we may deploy the system in rain or even snow. And lastly, something we also want to focus on today is interaction. Interaction generally could happen, for instance, between pedestrians and cars, as you can see here. And this is challenging because generally we don't have accurate models of interaction, and we don't know how to deal with that in terms of safe design of systems. Now, overall, these challenges raise the question how we can make these systems safer. We can ask questions about fundamental limitations that we're facing, but also what guarantees in terms of safety and performance we can provide for our algorithms. And we work broadly on these topics, but for today, I thought I would focus on a specific problem that we've been looking into for quite a while. And this is safe control design in dynamic environments with conformal prediction. Now, the exact problem is as follows. We would like to compute control inputs for our system so that it avoids dynamic agents in the environment with a probability no less than 1 minus delta. You could think about controlling a car so that it avoids pedestrians or other cars with high confidence. Now, why is this a challenging problem? Well, to begin with, the agents in the environment, they're uncertain and interactive, so they're generally difficult to reason over. They may have unknown intentions. And what one typically does is one uses these days learning-enabled predictors to predict their behavior. Okay, but it turns out that learning-enabled algorithms, they may not always be accurate and they can be imperfect. They can sometimes predict wrong things. And what we would like to do, hence, is we would like to reason over uncertainty jointly over agents and learning-enabled predictors and incorporate them into control design, which generally is challenging. Now, of course, there's some related work. Very briefly, there are, of course, motion planners such as graph or sampling-based methods. However, typically, these are static and ignore dynamic agents in the environment or don't reason over uncertainty. There's a lot of reactive control methods. You may have seen navigation functions, dynamic window approaches, or prominently also control barrier functions. Since these are reactive in nature, though, they don't use any predictions, and usually they apply to rather simple systems. And lastly, a lot of literature recently on predictive, interactive, and non-interactive methods using deep reinforcement learning, Gaussian process-based modeling and control. But here I would argue that typically they don't provide strong safety guarantees unless you make simplifying assumptions. And for us, the question then was, well, how can we quantify uncertainty of learning-enabled predictors rigorously and design safe controllers based on that? Now, that really begs the question about uncertainty quantification of learning-enabled systems. And since we are control engineers, we like block diagrams. So I try to abstract here a learning-enabled system as the block diagram. We have the system here. In this case, this is a car, an environment that may be dynamic, uncertain, and interactive. And we usually have sensors such as camera or LiDAR. And we use the sensor information for perception and prediction with a goal to get state estimates about states of the system as well as the environment. And these we then use within planning and control to compute low-level control actuation. And we repeat this over and over again online. Now, for this learning-enabled system, the question that I want to ask is, how do we reason about safety of such high-dimensional systems? And by high-dimensional, I mean that we may have AI models, learned models, specifically for perception and predictions that are complex, that may consist of thousands or millions of parameters potentially, right? So we can't compute anything in closed form or analyze in closed form anymore. Now, there's some work, for instance, using satisfiability modular theory solver, mixed integer linear programming techniques, or hybrid systems reachability to compute input-output properties of, let's say, neural networks or neural network control systems, for instance, reachable sets. However, these techniques, unfortunately, have scalability issues and don't apply to the complexity of the problem in hand. Now, this has motivated convex relaxations such as semi-definite or linear programming approaches. But since these are approximations, they're typically overly conservative, also don't apply to the problem in hand. Now, ideally, we would like to navigate this trade-off between conservatism and scalability. And on top of that, we would like to deal about stochasticity that enters this control loop. Disturbances on the system, noise on the sensors, or here particularly today, randomness in the environment. And that's when we, a couple of years ago, started asking ourselves, can we instead use more efficient statistical tools together with data to reason about safety of such systems? And what I want to argue here today is that what we need is an online monitor in between or some type of algorithm that does uncertainty representations using efficient statistical abstractions. And these statistical abstractions we want to build here with this tool, conformal prediction. So let me give you an introduction to conformal prediction. It gives you uncertainty quantification under minimal assumptions By that, I mean that to begin with, it's distribution free. So if you're in a supervised learning setting where you have inputs U and outputs Z that are drawn from some distribution calligraphic D, you don't need to make any assumptions about this distribution. It could be any funky distribution and doesn't have to be Gaussian. At the same time, you also don't need to make any assumptions on predictors that you may be using. For instance, if you have a predictor mu that maps an input to predict an output Z hat, mu could be a neural network, it could be something more sophisticated, or it could also be as simple as a Kalman filter. What you need, however, is the availability of an IID, so independent and identically distributed calibration data set consisting of k input-output pairs that are also drawn from this distribution. And the goal in conformal prediction then is the following. You want to fix a failure probability delta, so you do this as a user. And conformal prediction gives you a prediction region C, so that with probability no less than 1 minus delta, a new data point Z is contained in this region C. And the region C may also depend on the control input. So just to illustrate this, assume you're given 3 images shown here along with a classifier. Then the left image is the easiest to classify. It's a very simple task here. It's quite obvious. And in this case, the prediction region C would contain only one label and the correct one. Now, images 2 and 3 have a lot more visual distraction and are harder to classify. And in this case, the prediction region C would contain 4 or even 6 labels, quantifying the uncertainty and the difficulty of the task in hand. Now, how does conformal prediction work? It's based on a rather simple quantilemma, at least the vanilla version of conformal prediction. We assume here that we have k plus 1 IID random variables that are denoted by R0 to Rk. And these in the community are referred to as the non-conformity score, but you can just think of it as the prediction error for now. The goal now is to find a probabilistic upper bound for the test data point R0 in terms of the calibration data R1 to Rk. And in fact, what one can show is, again with probability 1 minus delta, that the test data point R0 is bounded by the 1 minus delta quantile over the empirical distribution of the calibration data R1 to Rk and infinity at it. So pictorially, how this looks like is as follows. You take your calibration data and you plot the histogram of the calibration data, meaning here on the x-axis, you have the values of the non-conformity score. On the y-axis, the frequency by which they hit on your calibration data. You plot this, and you simply take the 1 minus delta portion of this. If you really want to compute it, what you do is the following. You compute p, which is the ceiling of k plus 1 times 1 minus delta, and then you take the p smallest non-conformity score. So what you really have to do is you have to run a sorting algorithm and take the p smallest value. And this is computationally super efficient. You can run it online if you want to while the system is operating. It also has an implicit data requirement. Since you're taking the p smallest value and you have k number of data points, p is not allowed to be larger than k. And if you want to know an explicit bound, you can do some math and you see that the number of data is bounded by 1 minus delta over delta. And while we obtained a lower bound of 1 minus delta here, one can also derive an upper bound under the additional assumption that the non-conformity scores are, their distribution is continuous. And in this case, you get an upper bound of 1 minus delta plus 1 over k plus 1. And you see as k, the number of calibration data, goes to infinity, you sandwich your probability between 1 minus delta. Now, I think success of conformal prediction is really in the freedom of designing the non-conformity score and actually engineering the non-conformity score that you're interested in. On the previous slide, we didn't make any assumption on how this non-conformity score R looks like. So let me give you the most simple example in a 1D regression example. We could here, for instance, naively choose the absolute value between the error of your output and the predicted output. And then just applying conformal prediction gives you that for your test data, the prediction error is bounded by the 1 minus delta quantile over your calibration data. And then you can slightly rewrite this and you get a prediction region for your output Z, where the prediction region is centered at your prediction and has a width or a size of 2 times the 1 minus delta quantile. And I argue that conformal prediction is simple, it's general and efficient. Simple mainly because it's easy to understand. It's only the previous slide you need to understand. It's general because it applies to general black box systems as long as you have data. And it's efficient if you choose the right non-conformity score. And I want to give you some example of what this could look like. For instance, here an F-16 aircraft, and we wanted to compute reachable states for some time into the future. For some test data point, you can see the distribution shown in black over here. And importantly, you see for different choices of non-conformity scores, the prediction regions in orange, green, and blue. And all of these prediction regions capture, in this case, 95% of the data. And you could choose which of those you want to use. By the right score of the right choice of the non-conformity score, you can also capture multimodal distributions. Here, for instance, we had an example where a robot could go left, right, or straight with equal probability. So you get in green shown here these clusters of data that capture these three modes. And again, if you do it the right way, you can identify these clusters and fit ellipsoids shown in black here to the data that capture 95% of the data. So this is basically all you need to know to go ahead and use the vanilla versions of conformal prediction. But I want to give a small disclaimer because I realized that oftentimes the guarantees that you obtain are being misinterpreted or misunderstood. Conformal prediction gives you what's called marginal coverage guarantees, meaning that the probability measure that we talked about so far captures randomness in the draw over test and calibration data R0 to Rk. And this is in contrast to what we would ideally like to have, which is calibration conditional coverage, meaning we would like to look at the conditional probability, where we condition on the calibration data, and where the probability measure here now captures randomness in draw only over the test data. Unfortunately, however, these guarantees are impossible to obtain unless you make quite strong assumptions. The good news, however, is that, again, if the distribution of your non-conformity scores is continuous, you can interpret this conditional probability as a random variable itself, and you know that it's beta distributed with a mean of 1 minus delta, exactly where you want to be, and with a variance of 1 over k. So the more data you get, the better your guarantees become because the variance shrinks. And if after this talk you become interested in this topic, I mean, we recently published a survey paper where we talk about all of this in more detail, so feel free to check it out. Okay, with this, I would like to get back, now that we know about conformal prediction, about safe control in dynamic environments. And for now, we assume that there's no interaction between the control system and the environment, and we'll relax that later. Now, why should you use conformal prediction here? If we look at these three examples that I've shown here, we notice a couple of things. First of all, the system dynamics, they're quite well understood and then can be modeled accurately. So we don't really have issues in modeling, let's say, a car or a mobile robot. We're quite good at that. On the other hand, the agents in the environment, which are dynamic, are in general hard to model. Again, they may have unknown intentions, and it's hard to write down like equations for them. At the same time, though, we live in a data-rich world, and we have large data sets that may describe the behavior of such agents. And we also have very powerful learning-enabled algorithms that may be trained on such data. So what we would like to do is we would like to use all of this together with conformal prediction to design safe and efficient control algorithms. Before going into the details, I want to give you a very high-level overview so that you get the gist. Here, what we assume is that we have an offline trajectory data set. For instance, you may have observed how pedestrians walk over an intersection, and you have data of that. Okay. Now, online, while our system, for instance, a car, is operating to avoid these pedestrians, we assume that we observe the states of the pedestrians at time t. So this may be position and velocity, and potentially also history of that. Then we use a trajectory predictor that could be learned. So for instance, it could be a recurrent neural network to make predictions about the future behavior of the pedestrian, here denoted by y hat of t plus 1, y hat of t plus 2, and so on. The important question now, though, is how good are these estimates? Especially since we may be using learned components, the estimates could be accurate, but they could also be completely off. Okay. So what we would like to do is we would like to quantify uncertainty, and we do this with conformal prediction by computing these prediction regions, which are shown in blue over here, and which are statistically valid in the sense that they contain the future behavior of the pedestrian with a probability no less than 1 minus delta. Once we have computed these, we'll forward them to the robot where we assume to know the dynamics, and we design a safe controller. In this case, it will be a model predictive controller that makes sure that the safety constraint C that couples our system X and the agents in the environment Y to be non-negative. For instance, ensuring a minimum separation distance. And this algorithm has some key features. It's quite lightweight computationally. It has statistical safety guarantees. We can deal with distribution shifts, we'll see that later, and we could even consider temporal logic constraints, so more complex high-level specifications if we wanted to. Now, a little more in detail, I want to model the problem first. We model the environment as a random trajectory. So here, y0 and y1, the state of the environment at time 0, time 1, is drawn from a distribution calligraphic D that is a trajectory distribution and could be any discrete time stochastic system. So for instance, an MDP. And importantly for now, it's static. So there's no interaction where we would model interaction by a dependency on the trajectory of the control system X. So when I write D of X, that would mean interaction, just D means no interaction. Then we consider a trajectory predictor that maps observations up until the current time t into predictions of the future for some finite mission horizon time capital T. And here for the simulations, we use the social long short-term memory network, where we use one of these LSTMs for each agent, and then we pool them together to model interaction. And we mainly did this because we could download it from the internet. But the method really is model agnostic. You could use any generative model if you wanted to, any learned model, but you could also, if you have available, use a physics-based model. And just to remind you, in this setting now we want to compute these blue prediction regions. We have a couple of methods to do that, but I want to tell you about one that was particularly helpful and successful for us. Now here we define the nonconformity score as follows. We say that the nonconformity score is the maximum over all times tau that we predict into the future. And for all these times tau, we consider the prediction error. So the error between the state of the environment at time tau and the prediction at time tau. And importantly, we add a normalization constant here that will allow us to get some minimum volume prediction regions. I'll tell you a little more about that on the next slide. For now, yeah, you can ignore it. Then we apply conformal prediction to these nonconformity scores. And what we get right away is valid, statistically valid multi-step prediction regions, meaning that for a new test trajectory, the tau step ahead prediction error is bounded by the 1 minus delta quantile and renormalized by these alphas. And importantly, it holds for all times tau into the future. And just to illustrate this, we have a small example here where we predict a dynamic agent 20 time steps into the future, shown in blue here, and we have the prediction regions shown in green around it. You see these nice cone-shaped regions that really capture that uncertainty grows over time. In red, you also see a baseline that we compared against, and what you see is that the regions that we obtain are actually quite tight and have this minimum volume kind of flavor. And we see this even better if we look at the two-dimensional plot, where here for 1.25 seconds ahead into the future, you see the prediction errors shown in blue for some test data points, and in green, you see how we tightly capture, in this case, 95% of the data. Now, very briefly, I didn't tell you about how we choose these normalization constant, and we obtain them as the solution of an optimization problem. So what we do here is we enforce this max nonconformity score over our data. We minimize our quantile of the conformal prediction quantile, and we enforce some normalization budget to get some well-posed optimization problem. And if you think about this carefully, you notice two things. One, you can solve this problem offline, so you don't have to solve it online. And two, it's a mixed integer linear complementarity program. Why? Well, because the quantile, you can reformulate it as an inner linear optimization problem that you can then reformulate with its KKT conditions, which are basically linear complementarity constraints. And the max operator here, you can rewrite with a mixed integer linear program, okay? And with that, we have constructed these cone-shaped type prediction regions, and we can go ahead and we can do control design. And here, like I said, we chose a model predictive controller where at each time step, we observe the environment, we make new predictions about the environment, and we compute new prediction regions. And then we iteratively solve this optimization problem where we compute control inputs to minimize some cost subject to some dynamics, state, and input constraints, and a robust safety constraint that makes sure that for each state of our environment in these blue prediction regions, our dynamical system is safe. You can see here that this is again a bi-level optimization problem because we have an inner infimum here, and we can even reformulate this in closed form if C, the constraint function, is Lipschitz continuous. In this case, we just take C, evaluate it as a prediction, and tighten the constraint by the Lipschitz constant of the function C and the size of the prediction regions. Now, if and we can discuss this, but if the MPC is recursively feasible, we are then guaranteed to find a safe controller with probability at least 1 minus delta. Okay. Now, recursive feasibility, I would argue, is a general issue, an open problem in stochastic MPC. We have looked into it in like 2 directions. One being a shrinking horizon MPC, where we can modify these constraints to obtain recursive feasibility. And another one was more to, also in a statistical way, quantify what is the probability of being recursively feasible. Now, small toy example that we implemented here, we have a mobile robot that navigates around 3 dynamic agents. What you can see here is basically that we build these prediction regions in green that are cone-shaped and that shrink over time, which allows us to plan an optimal path here for the robot. We also implemented this in Carla, autonomous driving simulator, where we have pedestrians that spawn with random initial positions, have random goal positions, and walk at random speeds. And this was merely to validate empirically our theoretical guarantees. And we validated it for the 1 step ahead predictions, which checked out. We also ran the MPC for 100 times, where we observed only 1 safety violations, while theoretically we were guaranteed to have not more than 5. Interestingly, we also did a comparison with the Gaussian process to contrast a little the kind of frequentist guarantees that we obtain with the kind of Bayesian guarantees that or approach that you have in GPs. And in our case here, the GP actually largely undercovered. It had only 70% coverage. Okay, so this was safe control in dynamic environments. But what I would like to do next is I would like to look into interactive environments. So where the control input that we apply to our dynamical system may affect how the environment behaves, the dynamic agents in the environment. And this then becomes an instance where control really changes the data that we're receiving, which is again the title of the talk here. So what we want to look at now is at the following question: what if interaction between the control system and the dynamic agents changes the distribution of the dynamic agents, of the behavior of the dynamic agents? And this can easily happen, right? If we, for instance, look at self-driving cars again, if the cars come too closely to a pedestrian, the pedestrian may halt or, basically change its behavior. And what happens in that case technically is that all the safety guarantees that we derived before would be thrown out of the window. They would be gone. Now, you can quantify how much the safety guarantees degrade, but technically you don't achieve your original goal anymore. And this is because of a chicken and egg problem, where on the one hand side, you have your dynamical system described by the equations of motion of this system, while on the other side, you have your environment that is described by a distribution D that now depends on the trajectory of the dynamical system. And this causes a distribution shift where, depending on the trajectory of the dynamical system, the distribution of the environment, so of the behavior of the environment, may change. At the same time, though, the behavior of the dynamical system is given by the control or influenced, controlled by the control law, which is a function of the prediction regions, these blue prediction regions, which is a function of the data that we are receiving. In other words, the environment is a function of the control system, while the control system is a function of the environment or of the data of the environment. And this creates a circular problem that makes it difficult to reason about safety. Okay. And what we were wondering is the following: if we can iteratively update our controller to break this circularity and maintain safety. And before going into the details, I want to give you a sketch of of the idea that we're implementing here. We're again assuming that we have the pedestrian, and we again have a trajectory predictor that makes predictions about the future behavior of the pedestrian. But now what we assume is that we have we set them ourselves, very large prediction regions that have a radius of C0. And they're so large, these predictions, that they're safe. So we again have the property that if we deploy the controller pi, that is a function of this radius C0, we obtain safety with 1 minus delta probability. And since the controller is safe, we can go ahead and we can deploy it in the environment to collect some data under this controller. And with that data, we can go ahead, we can apply conformal prediction, and we hopefully get prediction regions that are a little smaller, here of radius C1. And we have to do that in a way that the new controller the new policy, pi of C1 is still safe with 1 minus delta probability. Because then we can again go ahead, we can collect new data under this policy. We can again apply conformal prediction, and hopefully again we get prediction regions that are a little smaller while being safe. And the idea is then to rinse and repeat this procedure until we converge to hopefully a fixed point of this algorithm. Now to formalize this a little more, like I said, the idea is an iterative control update scheme where we denote our policy pi of Cj, where j denotes the episode j. And in this case, we again focus on optimization-based controllers, where we compute a control input sequence that minimizes some cost, subject to some dynamics, as well as some robust safety constraints shown here. But now this robust safety constraints changes at every iteration of our algorithm, because these blue prediction region depend on the size or the radius of the prediction region Cj. A brief disclaimer here, everything that I'm presenting now is controller agnostic. So you could use any controller pi that is a function of the radius Cj that keeps the system safe, but we for now simply focus on this optimization problem. Now the main task in the remainder is the following. We would like to update this radius Cj of the prediction region to achieve three design objectives. First of all, we would like to have episodic safety, meaning that at each episode, we want to make sure that the trajectories that we obtain under the controller pi of Cj are again safe with probability 1 minus delta. Okay. Additionally, we want that we improve performance across episodes, so we're getting better performance. And we also want that we eventually converge, our algorithm eventually converge, in the sense that the size of the prediction regions converges. And what we were wondering is if we can use robust conformal prediction to update the radius Cj safely. Now, so far when we talked about conformal prediction, we really assumed that we have IID data. But now we're in a setting where the data may potentially be dependent or not identically distributed. And luckily, there's a very active community in conformal prediction that has brought a lot of variants of robust conformal prediction that can deal with non-IID cases. And we will focus here today on adversarially robust conformal prediction. But again, there are many more. And if you're interested, we've summarized them in a sidebar in our survey paper with the references to the original literature if you're interested in that. Now, how does adversarially robust conformal prediction work? We consider here perturbed nonconformity scores. So we consider the nonconformity score R over the trajectory Y, but plus some perturbation delta. And we want to make sure that for all perturbations, this perturbed nonconformity score is bounded by the unperturbed nonconformity score plus some constant m that we need to know. And adversarially robust conformal prediction then tells us that for a test trajectory, the perturbed nonconformity score is bounded by the empirical quantile over your non-perturbed data. So this is standard conformal prediction plus this constant m. And this idea of adversarial conformal prediction motivates our iterative robustification approach that looks roughly as follows. Like I said before, we initialize our controller in a safe way by choosing some conservative prediction regions. So like we start conservative and safe, and we want to remain safe, but get less conservative over time or across episodes. Then we collect data, we deploy this controller, and we use that data to apply conformal prediction. So we calibrate and we compute this 1 minus delta quantile. The next step is that we want to robustify. We need to compute some constant m that I'll talk more about on the next slide. And then we update our controller using the conformal prediction result and this constant m. And then we repeat this over and over again. And here you can see some simulations that we did where these prediction regions shrink over time. Now, I want to detail the algorithm on how we do this more precisely now. Like I said, the first step is to collect data, and nothing really changes there. It's like in the first part of the talk, we deploy our system with a given controller and we collect some data. The only thing that changes here is now we have a subscript j for the episode that we're in. The next step is to apply conformal prediction, so to calibrate. And this is also exactly the same step as before. We simply compute the 1 minus delta quantile over our nonconformity scores, which is again this max nonconformity score. The next step, though, is a little different. And for that, we first need to note something, namely that the nonconformity score at the next episode minus the nonconformity score at the current episode is bounded by the Lipschitz constant of the dynamics of the environment. So here we make an assumption that the dynamics are somewhat continuous. So that, again, that this is bounded by the Lipschitz constant of the dynamics times the difference in the control inputs at the next episode and at the current episode. And we denote this as mj plus 1. With this observation in hand, we immediately know from adversarially conformal prediction that the nonconformity score at the next episode is bounded by the quantile over the nonconformity scores at the current episode plus this constant m. And this holds with 1 minus delta probability. And this, in fact, motivates the choice of updating the radius of the prediction regions. Namely, we choose that the radius at the next episode is larger than what's on the right-hand side here. So larger than the quantile of the unperturbed of the data at the current episode and this constant m. And if we do this, we immediately obtain that the policy pi of Cj plus 1 is episodically safe. And this is great, right? But there's a small catch to it, because if we plug back in m into this equation, we see now that the radius Cj plus 1 appears on both hand sides of this inequality. So solving for this actually be a little more tricky. We have two methods to do this. We use numerical solvers using bisection methods. So that's one approach that we're choosing. Or if we know that the policy pi is Lipschitz continuous, we can further simplify this and basically rewrite m, so this condition here, by L pi, Lipschitz constant of the policy pi, times Ly times the difference in the size of the prediction regions. And this will be useful down the line because it will give us an explicit equation about C of j plus 1. Okay. Now, in summary, we have obtained episodic safety. We haven't talked about convergence of the algorithm yet, but before doing that, I would like to show you some simulations and give you some statistics, some metrics. So the first one is a quite academic example where we have a car-pedestrian collision avoidance example. So very simple. And the plot that I'm showing here may look convoluted at first, so let me walk you through it slowly. On the x-axis, you see the number of episodes that you're iterating over your algorithm. On the y-axis, you see the coverage that your prediction regions actually have. And in blue, you see our algorithm. And what you can observe is that across all episodes, we have the desired coverage of, in this case, 90%. For some of the baselines that we implemented here, you see that at least at one episode, we don't achieve the desired coverage in terms of our prediction regions, okay, potentially violating safety down the line. We also have here in this plot the empirical safety coverage of our algorithm, which is 100% in this case at all times. And we also plot how the radius of the prediction regions evolves over episodes. So here you see we're eventually converging, and the same for the cost of the controller that is also eventually converging. And again, I'll talk about convergence conditions after I've talked about simulations. Now, this was a rather academic example. So we also implemented this in QuadSwarm, which is a drone simulator from one of my colleagues at USC. Here, what we have is 5 uncontrollable agents that are controlled by RL algorithms that model and take into account interaction for navigation. We also have an ego drone that deploys the policy that I just explained, pi of Cj. And additionally, it's filtered through a tracking CBF controller, which we needed for these simulations. If we again look at the metrics, we again see that across all episodes, we get our desired coverage of the prediction regions. The same for safety. And we again see that the radius of the prediction region, as well as the performance, converges. And while I've shown the plots before, I just want to briefly reiterate here or illustrate how the prediction regions of one of the drones could look like, shown in blue here, and how a path or a control input, control trajectory could look like for our ego drone. Okay, so I want to finish now this with talking about convergence conditions. And this is going to be a little more mathy, but I think it's interesting to see nonetheless. Recall that the update rule for the radius at the next episode looked like this, and that we also talked about the case where the policy pi was Lipschitz continuous, in which case we could look at this condition. And with this condition, we can first define what we call a closed loop gain. So we say that the product of the Lipschitz constant of the controller and the dynamics is a closed loop gain kappa, okay? And now, if this closed loop gain is below 1, we can derive closed form solutions for this update equation of the radius. So we have two branches basically that are closed form again that tell us when the radius at the next episode is smaller than the current radius or when it's larger. And since we have this closed form expression, we were wondering if we can use these to analyze convergence of our algorithm. And if I ask that way, then the obvious answer is yes. Now, if we want to talk about convergence of an algorithm, the first question is convergence to what? So we need to define some form of a fixed point. And in order to do that, we will look at the true quantile. And recall that conformal prediction considers empirical quantiles over data, but there is an underlying true quantile that we may not know or be able to describe. So what we do here is we take the cumulative distribution function of our nonconformity score at the 1 minus delta level, okay? And if we assume that this true quantile has a fixed point, meaning we have a C star that if we plug it in, we get a C star out, we can analyze convergence under the assumption that this quantile is continuous, which is actually, there are quite mild assumptions. And particularly what we can show is that the difference in the radius at the current episode and with respect to the fixed point is bounded by two terms. The first term is basically a function of the initial discrepancy between C0 and the fixed point. And the second term is an error between the empirical and the true quantile that we have. And for these, you can get actually high probability bounds. Now, with these kind of convergence guarantees for the radius, you can even derive performance bounds for your performance under additional assumptions on monotonicity of your performance function. And this basically wraps up my talk. I just have one more slide that I briefly wanted to mention because we have a CDC submission here, where we try to think about if we can generalize these ideas. And by ideas, I mean using robust conformal prediction and a kind of iterative control update approach to different problems in control. And here we focus on robust control design, which then turns out to be another instance where control changes the data that we're receiving. Now, very briefly, in robust control, what we typically do is we use knowledge of a known error bound between f hat, which may be a model of the dynamics that we have, and f, which are the true but unknown dynamics of our system. And we call this error bound typically delta, and we assume to kind of know this in practice. We kind of assume to know this in theory, but in practice, we may actually not know it. It's often used as a tuning knob. We select some delta until the algorithm works well, or sometimes it's even estimated from data. But in any case, you can't really reason about safety. But what is a good starting point to begin with is to estimate delta. But if you do this, it again creates a chicken and egg problem where yet again, on the one hand side, you have your dynamics of the system, okay? On the other hand side, you now have a model error, delta hat, that depends on the trajectory of the control system, while again, the control system through the controller depends on delta hat. So again, it's a circular issue where the model error depends on the system depends on the model error. And in our CDC paper, we again attempt to break this circularity and provide closed loop guarantees by using robust control barrier and control Lyapunov functions. So I don't want to go into detail about this. Some of you may have seen these conditions, but we basically convert them into high probability guarantees for our system. And if you're interested, this should come up on arXiv quite soon. And with that, I'd basically like to end the talk. Thank you all for joining. Thanks for the invitation. And if you have any questions, feel free to ask now or send me an email.
Okay. Yes. Thank you for the great talk, Lars. Any questions from the audience? Feel free just to unmute yourself, and also from the lecture room. Okay, so is there any questions from the audience? I can maybe start one. Actually, I have you. Maybe start the first one. So, Lars, I see you only use data to build these sets with very minimum assumptions for the underlying probabilistic structure, right? So that's remind me of set membership method to building all these uncertainty sets, where we can also work on pretty general functions. But of course, we don't have a probabilistic way to build to argue the uncertainties, the guarantees. Do you see a connection there between these two? If I solve all these probabilistic settings in your framework, do you see a connection to set membership?
I think there is. I have to, I guess, preface this by saying that I'm not an expert in that topic. I don't think I've read a lot about it. But the way I understand this is that conformal prediction is a layer that you can put on top of like heuristics or approximations, right? Or when assumptions break, right?
Yeah.
So I think you could use this as a base algorithm to get shapes that may indicate membership in some sense, right? But they may only be valid under some assumptions. And when those assumptions break, they may not give you coverage, they may be wrong. And you could use them though as a baseline for conformalizing on top, because then you have some data and you get probabilistic guarantees even when the assumptions break. So I think it's actually complementary. In the same way, I see, like people ask about Kalman filter, for instance, very powerful, works in a linear setting with Gaussian noise. There are nonlinear extensions, but it's the same thing. Nothing prevents you from using a Kalman filter as a good base guess. And when the standard assumptions break, you conformalize on top, and you extend or shrink the prediction regions depending on the effect of the nonlinearities or the distribution that you actually have. Yeah, that's also, I think, why it's really powerful, this tool, because it's more complementary to a lot of approaches out there, especially in learning. I mean, in the AI community, they're using this a lot. I think for exactly that reason. Yeah.
Any other questions?
I had a question.
Oh, yeah, please go. Please go ahead.
Hi, Lars. This is Argo. This was a very nice presentation. I wanted to ask, have you compared your method with a distributionally robust MPC? Because the idea behind there, I mean, if I'm talking about purely about the performance, the end job is somewhat similar, if I can visualize, because when the multiple agents interact, you sort of looking for some sort of distribution with inside a ball, and you train your controller in such a way that it performs certain sense. This is my first question, and I have another question, which is more on a philosophical side, just to think about this, because what you say here is that your control changes the data and you use the data to further, you want to break this loop. So have you thought about the direction, like where you take inspiration from the game theory? Because when you talk about the multiple agents, if you consider that their actions you can embed inside your controller, and of course you want to embed using the data that you observe, then I'm just thinking like can that line of thought also be utilized in this kind of setup? Thanks.
Yeah. Can you remind me of the first? I forgot the first question. I remember the game theory.
First question was about, have you compared your method with the distributionally robust MPC?
Yes. No, very questions are very on point. So with DRO, it's a very related technique. The same with scenario optimization, obviously. The thing that is different in DRO is you have to select the size of the uncertainty set. And you generally don't know how to do that, even when you don't have a distribution shift, right? Like if you say the distribution doesn't change, you don't have good ways of selecting your ambiguity set. It's often a tuning knob as well, right? And then the second thing is, if you have distribution shifts, the ambiguity sets, they may increase further. So I haven't seen works that use DRO in interactive settings. So I guess two answers to that question is, in the dynamic setting, when there's no distribution shift, I see a difference in the sense that in DRO, you directly optimize for control inputs, but you have to kind of guess the ambiguity set. You capture some part of your data. And in the distribution shift setting, it's a similar issue, right? So there's certainly similarities, but I think these are different approaches. And we haven't compared them yet, so that I should also say. So I see this as a complementarity line of work, and I mean, I really hope eventually that there's a better understanding of these tools and how they are different or similar. Regarding the second question about game theory, this is also something we've been thinking about, but we haven't been doing it yet. So I don't have good intuition there, but it would be very interesting to embed it into a games type of setting, potentially also then getting less conservative. But this is all something I think that would be good to look into. I hope this answers the questions roughly. Not super precise answers, I guess, but yeah.
Thank you for the answers.
We have one question from the classroom. Gabriel, maybe you could come closer to the.
Hi, Lars, can you hear me?
Yes.
I have a quick question about if you can comment on the difference between this conformal prediction, maybe the vanilla version, and the scenario approach in general. I think I missed the difference there.
So I would say scenario optimization is a tool that does something different, right? Like conformal prediction only computes uncertainty of, let's say, a predictor or of a non-conformity score. Scenario optimization directly solves an optimization problem. There are papers that establish in some shape or form results that under some conditions, you can formulate a one-dimensional scenario program that recovers vanilla conformal prediction results. So there are connection between these, right? I see conformal prediction or other like concentration inequalities more generally as a way to quantify uncertainty here of neural network predictors. So again, there are many connections between all these statistical tools, and it would be good to understand these a little better. For me, I'm I guess a little more application driven. I look at what fits best, and for this problem here, where we have a neural network predictor and you just want to compute these prediction regions, I think conformal prediction is the simplest tool that you can apply to the problem.
Hey, thanks. You can ask another.
Sure.
Another one is related to the horizon, right? Because if you're using this to estimate trajectories of dynamical systems or agents, and then you pick a horizon capital T, and if I understand correctly, all your predictions are valid until this capital T. But as you are running your system in real life, there's this recurrence kind of part. How does it work with the recurrence? I think you get my question. How the guarantees work with the recurrence?
Yeah, that's also a really good question. So I've been on purpose a little sloppy in the presentation. In the MPC case, what you have to do is you have to recompute the prediction regions. And what you do is you define a non-conformity score that only takes into account the one step ahead prediction at each time t where you recompute your controller. And by that, you get guarantees. So technically so the way I've presented is you get prediction regions for at time 0 for all steps, or at time t for all steps that you predict into the future. And then, if you solve it at the current time, you get some guarantees. But what you do really to get these guarantees is you compute the prediction regions at each time step t, and you get a joint guarantee over these, so that when you recompute your controller, you're statistically valid at each time t when you recompute it. So there's a catch to it, let's say.
Okay.
So I can point you to it, but again, the high level idea is at each time t, you only need that the prediction region at the next time step is valid, right? Because you're computing your control input now in an MPC. If the prediction region at the next time step is valid, you know that if you apply the current control input, you will be safe at the next time step, okay? You do that, and then at the next time step, you repeat that procedure. So technically, in an MPC, only the one step ahead prediction region is of importance.
Yeah, I see your point. Okay, thanks. I think I get it.
Yeah. So this is a bit the reason why I presented it, because I'm deliberately a little more abstract, and usually I gave a longer talk, and then I have first an open loop version where I use the tau step ahead prediction. And then, you move to a receding horizon controller where then only the one step ahead predictions become important. It's just, I feel it's a little more difficult to explain, and I think this abstraction works a little better.
Yeah. Okay, we have another question from Mohammed.
Hi, Lars. Thanks for your fantastic and awesome presentation. It's very nice. I have a quick question. Generally, we have this assumption of IIDness for the guarantees. Like it happens in the RO, it happens in the scenario approach. And also, I noticed that here you have similar assumption most of the cases. What really bothers me slightly, is that when we have a closed loop, how we can maintain such assumption, or how you break the chain of this like chicken and egg of IID and IID here.
Yeah.
Thanks.
It's basically, this is really the point of the third part of the talk where we don't have IID anymore. There's a catch to it, right? The important part is, let me just go there, is exactly this here. And the catch is you need continuity of your dynamics, okay? You need to know a Lipschitz constant, so it's a worst case argument. That's why the algorithm here is potentially conservative. So let me make 2 points. I believe that an iterative approach with robust versions is a good way to go and break the circularity. The approach that we've chosen here, the technical one, may be conservative. Okay, so I think there are 2 things. One is the idea of iteratively breaking this, which I think is really good, and we're continuing on that. The other one is using adversarially robust CP, and this has the drawback of potentially being conservative, and we need to assume continuity and no Lipschitz constant here, right? And there may be ways of doing this less conservatively. But under this Lipschitz continuity assumption, you can bound the nonconformity score again at the next step, right? And then you can deal with non-IID data. But it's in a very adversarially, that's why it's called adversarially robust conformal prediction, right? You need to know what's your worst adversary. I hope this, gives the...
Thanks, I got the trick.
Yeah.
Thank you.
So it's quite interesting because we're working with Ricardo Sanfelice on hybrid systems. And we didn't anticipate, it's logical now, but hybrid systems are discontinuous in some way, right? And it's quite a technical challenge to make it work there. But it's interesting, yeah.
Thanks a lot. Thank you.
Given the time, I suggest we conclude the seminar. I would like to thank Lars again for his great talk. I think we will see each other in future conferences.
Definitely. Thanks a lot. These questions were actually really great. Appreciate it a lot. And hope we see us at IFAC or ECC and can chat a little more.
Yeah. See you. Bye.